Okay, humans, here we go. Linear inequalities. Not a linear equation, but a linear inequality. So something of the form y equals mx plus b, except for instead of an equal sign, you might have a greater than equal sign, or you might have less than or equal to sign, or you might have strictly less than or strictly greater than. One of these signs will replace the equal sign. Okay, well, what does that mean? Let's remember what it meant to have this. When we have y equals like 3x minus 2, that means we're interested in the values of x and y that make this particular linear equation true. So if you were to graph this, you go to -2 and use your slope to move from there. Use your slope of up 3, 1, 2, and 3 over 1. We're right in here. And it's this line that we're interested in. And it's all the points on this line. Any point on this line will provide an xy pairing that makes this equation true. But when we change it, when we say y is greater than or equal to 3x minus 2, good thing we graph the same exact line. However, we're interested in a different result. We're not just interested in the stuff that's equal to, right, y equals 3x minus 2, but we're also interested in the y's that are greater than 3x minus 2. And if we had an x that went in here and a y that went in here that made this inequality true, it would satisfy. So it would be a part of our solution. So what I like to do is I like to test a point. 0, 0 is a convenient point to test where x is 0 and y is 0. The point 0, 0 is a great test point. When you put that into the inequality, you can see that you've got this statement now, where this is going to become nothing, right? And you still have 0 on the left is greater than -2. Is that true? Yes, it is. If you test a point on a side of the line and it works, all of the points on that side of the line will work. So you can take any point that lies above this line, any xy coordinate, this point, or this point, or this point, and if you plug the xy pairing into the inequality, it'll give you a true statement. Pretty crazy, right? Let's do another one, see if we can make sense of this. Here's an inequality, however, it's not in y equals mx plus b, or slope-intercept form. In order to put it in slope-intercept form, perhaps we subtract 2 from each side. And now you can see that you're looking at the inequality y less than 2x minus 2. Okay. If we wanted to graph this inequality, since it's in slope-intercept form already, go to the intercept, the y-intercept, and then use your slope to move from that point. Up 2, 1, 2, over to the right, 1. Be careful here. When you have an inequality symbol that's strictly less than or strictly greater than, your line will be dashed. If you have an inequality that's greater than or equal to, or less than or equal to, or greater than or equal to, your line will be solid. And it'll become obvious in a second why that's the case. So these are 2 points on your line, and since we have strictly less than, we're going to graph our line with a dashed line. Now why is that true? Why is it dashed and not solid? And remember, these inequality symbols are consistent with open circles. These inequality symbols are consistent with closed circles on a number line. Because you're being inclusive in the statement below the red line, but above the red line here, you're being exclusive. You're not including those numbers or those values. So returning to our line, if we think about this point here in red, that's the point 1, 0. If you put the point 1, 0, 1, 0, into your inequality statement, you'll have 0. 2 times 1, negative 2. 0 less than 2 minus 2. Is 0 less than 0? No, it's not. So the point 1, 0 is not a solution for this inequality. So we're going to represent the line as a dashed line, indicating that the xy pairings, or the ordered pairs on the line, are not exactly solutions. Well, what is a solution to this linear inequality? Let's test a point and see where our solutions lie. If you look at the point 0, 0, a convenient test point, and you plug in the point 0, 0 to your linear inequality, you'll see that when y is 0 and when x is 0, what happens? 0 less than 0 minus 2. Is 0 less than negative 2? No. So that's not where your solutions lie. But what if we try a point that's on this side of the line? This is the point 2, negative 2. This point right here. And if we plug that into the original inequality at 2, negative 2, would that make a true statement? And you can see that on the left you have a negative 2, and on the right you have 4 minus 2 is 2. Is negative 2 less than 2? Of course. So since a point worked that's on this side of the line, you shade this side of the line. All the points that are on the right side of this line would work for this original inequality in blue. One last example. We're going to do it super quick. Here we go. The y-intercept is 1. Bang. The slope is 4, negative. So you go down 1, 2, 3, 4, and over 1. Your line is a solid line because your inequality says greater than or equal to. So the solutions for this inequality, there are solutions that lie on the line. Every single point on this line is in fact a point, an xy pairing, that when substituted in here will make this statement true. We've also got to find out what other ordered pairs would make this statement true. Grab a test point. Now it's kind of fishy right around 0, so I'm going to grab this point, 1, 1, and see if 1, 1 works or it doesn't. If it works, I'm shading on that side of the line. If it doesn't work, I'm shading on the other. So let's test it out. Where x is 1 and y is 1. Take the original inequality. Take your test point of x being 1 and y also being 1. When you substitute in, you've got this statement. And so is 1 greater than or equal to negative 4 plus 1? So is 1 greater than or equal to negative 3? Yes, it is. So let's shade on that side of the line. The shading is representing all of the xy pairings that will make the inequality true. And in this case, xy pairings that work are also on the line. Yay!